Okay, we've got some more chemistry to discuss. We're going to be moving pretty quick because most of this is review. So these are reactions of monosaccharides. So this is an excellent review of chemistry that we've seen in the past. So monosaccharides by themselves tend to be fairly soluble in water. So for example, this is very soluble in water due to all the hydroxyl groups. And so if you want to use them in synthesis and dissolve them in an organic solvent, they don't play very well. So what you can do is you can acylate them. And so you can use excess acetic anhydride. And so this reaction is an esterification. And so what you do is you mix it with the excess acetic anhydride, pyridine as a base, and on each of those OHs, you'll actually end up with an acyl group, this AC. And an acyl group is just short for this group here, coming from acetic, or the common name for like acetic acid. So that is an acyl group, and that would appear on each one of those OHs. And you can also convert each one of the OHs into an ether through a Williamson ether synthesis. Now, the ether linkages are much more robust than ester linkages. So it makes carbohydrates easier to work with if we can convert those polar functional groups into non-polar functional groups. And so down here in the bottom box, you can actually see the mechanism, which is simply, again, converting an alcohol into an ester by reaction with acetic anhydride. Chemistry that we've seen before in the carboxylic acid chapter, and the only difference here is that we do it many, many times. So the key is that we would actually convert each one of these OHs in here into an acetyl group. And so you can see that over here. Okay, and for the ether formation, what they use is silver oxide, and it just is beneficial because you can't deprotonate the sugar with sodium hydroxide, or you can't have, in the presence of this reaction, a good nucleophile. So we can't really have a strong base around. Otherwise, it would do an SN2 with the methyl halide. So using silver hydroxide, it does something really interesting. Silver halides tend to be insoluble, have a lot of affinity for each other. You may remember that from general chemistry. And so what the silver does is essentially strips that iodide off of the methyl group, making it much more electrophilic. And so you can get an SN2 reaction. It also generates in water small amounts of OH minus, and then that OH minus can come and deprotonate once you have added the methyl groups on all of the OH groups. So again, use excess methyl iodide and silver oxide just through a Williamson ether type synthesis, and every OH turns into a ether linkage. And ether linkages, again, are much more stable. There's only a few reactions that ethers undergo, but esters can actually be readily hydrolyzed. Okay, as a review of some things that I've said before, I talked about epimers. The definition of an epimer is a compound that differs from its relative by the configuration at one position. So sugars actually have many chiral centers. And so there are groups of sugars, such as mannose and glucose, that only differ at one stereocenter. Now, they're not diastereomers because, well, sorry, they're not enantiomers because enantiomers have to be complete mirror images. They are diastereomers of each other, non-superimposable, non-mirror images. So they are diastereomers, but they're diastereomers that only differ by one of the chiral centers. And so there's a new term for that, which is referred to as epimers. So epimers are diastereomers, but diastereomers that only differ at one position. So mannose and glucose are epimers, and glucose and galactose are epimers. And so in our bodies, we can actually take advantage of enolate chemistry to undergo an epimerization, or the process of making epimers. And so our body actually uses this procedure. And so from one sugar, you can actually convert it into another through enolate chemistry. As I mentioned before, enolate chemistry is very applicable to biological chemistry. And so if you remember, if we have a carbonyl, the alpha proton can be acidic. And so if we treat it with a base, we end up with an enolate. And the enolate can either be drawn with that negative parked on the alpha carbon, or we can draw it in the resonance form where the negative is on the oxygen. Now, if you notice, these enolates are a little bit different than what we've seen before, because off of this enolate, we also have an alcohol. So this is an enolate alcohol. And what's interesting about it is if you go and then retautomerize, so those electrons come down and you grab that H, you could add that H to either side. You could add it either to the right side or you could add it to the left side. If you add that H to the left side, then you're just back at glucose that you started with. If you happen to add it to the other side, then you've made mannose. So you can actually convert glucose into mannose under enolate chemistry. You just enolize and then you tautomerize and place the H on the other side. Again, our bodies have catalysts that do this very efficiently. If you just did this in solution, just took glucose and threw in some base, you would end up with a mixture of glucose and mannose. And actually, to be honest, several other products. So no epimerization is just enolate chemistry, and you can change the configuration of the alpha carbon right next to that carbonyl. And so you can imagine on keto sugars, this would also work. So in fact, how would we convert an aldose to a ketose? Again, just enolate chemistry. First step is exactly the same that we talked about, where you deprotonate and you form the enolate, as we see here. As I mentioned, these are kind of different enolates than what we've seen in the past. So they're actually alcohol enolates. So instead of just having an R group off of here or an H, they actually have another OH. So if we happen to protonate this enolate, we end up with an enediol. So we actually have two different alcohols off of that double bond. Now, if we know anything about enols, is that they can tautomerize. Well, we could tautomerize and pull that H off of here, and that would get us right back to an aldo sugar. Well, what happens if I actually tautomerized using this alcohol down here? Well, if we did that, and you can see the process here, we would end up with a keto sugar. So through enolization, you can actually convert from aldoses to ketoses. And so again, our body will do this, and you can convert glucose into fructose. So we can see two things, two applications of enolate chemistry. We can make epimers, or different sugars, and we can also make convert between aldoses and ketoses. So again, chemistry that we've seen before, but applied to sugars. And again, very biologically important, because this is how we do it in our bodies to convert sugars from one type to another. Now, again, another review of chemistry that we've seen before. We've talked about hemiacetals, how we can actually form these cyclic pyranoses and furanoses. But if you remember back in the ketone aldehyde chapter, we could go from a hemiacetal to acetals. Well, this is a hemiacetal. it's got a carbon-oxygen-carbon OH bond. COCOH, that's a hemiacetal. And so we can convert hemiacetals into COCOC bonds. COCOC bonds, those are referred to as acetal linkages, where the COCOH bonds are referred to as hemiacetal linkages or functional groups. And so we can do this on sugars. Instead of hemiacetals, they actually refer to it as a glycosidic bond now. And we'll see this change in nomenclature again when we talk about proteins. We refer to that in organic chemistry as an amide bond, but biochemists refer to it as a peptide bond. Here, we would refer to this as an acetal. Biochemists refer to this as a glycosidic linkage. So in this reaction here, we'll look at the mechanism in just a second, but if you take methanol and a little bit of acid, you actually get a glycosidic or a acetal linkage. Notice we actually get both anomers. And in this case, we actually get the alpha anomer a little bit more. This is a little bit more advanced topic, but it's referred to as the anomeric effect. So we don't always get the equatorial. There is some electronic interaction with this carbon here. And so for glycosidic bonds, actually the alpha is quite frequently favored just due to some more advanced electronic effects and interaction between the electrons on this oxygen and the anomeric carbon and the group off of that anomeric carbon. Since it's advanced, you don't really need to know it, but you may just be asking why the alpha is actually found in higher concentration. And it is referred to as the anomeric effect. Okay, but the key here is when we form this glycosidic bond, we actually get a mixture of anomers. That is the take-home message. So the question is, well, how does this work? Well, it works just like it did in hemiacetals back in the aldehyde and ketone chapter. We would protonate the alcohol, make a good leaving group. The adjacent electrons kick out that good leaving group. We end up with a C double bond O and a positive on that carbon. And the way to quench that positive on a carbon is to have another alcohol attack. And that alcohol can attack from either the top or the bottom. Let's just follow it attacking from the bottom. When it attacks from the bottom, since it was neutral when it attacked, it has an extra H. And we just need to pull that off. And once we pull that H off, we have our glycosidic bond or an acetal. The OH from the alcohol happened to attack from the top. We would get the beta anomer, and again, we'd just need to deprotonate and would have our beta glycoside or our beta glycosidic linkage. And this is an alpha glycoside. So if you take an alcohol, you can actually have it react to that anomeric carbon and make a glycosidic linkage. So in the last two cases, I've shown reactions with methanol and ethanol. In most situations, we don't have a lot of methanol floating around our biological system. If you do, you're probably blind and on your way to death. And if you have a lot of ethanol floating around your system, you're probably a college student. So that is not the typical alcohols that form glycosidic linkages. In fact, think and try to figure out what type of molecules we have that are alcohols, lots of them that are floating around in our system. And the answer is not too hard. We've got lots of sugars floating around in our systems. So as I mentioned, we really don't form glycosidic linkages with methanol. Hopefully that's not an alcohol you have floating around in your system. And so this arrangement, though, of carbon, oxygen, carbon, oxygen, carbon is actually the acetal linkage. But as I mentioned, those acetal or glycosidic linkages in biological systems typically aren't with methanol, as we see here, or with ethanol, as we see here. Now, there is another piece of nomenclature that we need to talk about, and that is reducing and non-reducing sugars. So if you have this acetal linkage, you're actually referred to as a non-reducing sugar. Hemiacetals here are reducing or can be oxidized. This linkage here prevents oxidation. And so they're known as non-reducing sugars. This right here is known as a reducing sugar. So let's take a look at that a little bit later. So that is some of the chemistry that we can do. We can form acetals with sugars. And again, we'll come back and talk about that soon. Some other reactions that we can do with sugars is, again, chemistry that we saw back in the aldehyde and ketone chapter, is we can form cyanohydrins. So if we take a little bit of an acid, what really happens is we deprotonate HCN, and that activates our carbonyl. And when the carbonyl is activated, that allows the nitrile to come in and attack. And this carbon right there is the same as that carbonyl. And so we end up with these cyanohydrins. The nitrile can attack either the top or the bottom, so we end up with two epimers here, where the OH in this case could be off to the right, or on the case below, off to the left. Now, we talked in the amine chapter about how we can reduce nitriles. And typically what we did is we reduced them all the way to amines. Now, if you're very careful and do a Lindler-like reduction, you can actually just reduce it once. And if you reduce it just once, instead of going all the way to the amine, we go to the imine. And so, interesting now, what we've got is two imines. And again, what we've learned back in the aldehyde and ketone chapter is if you mix an imine with water, it hydrolyzes into a carbonyl. So look at this amazing transformation. What we've done is we've added an extra carbon as a nitrile. That carbon we've turned into an imine, and then that imine we've turned into a aldehyde. We've actually extended the carbon chain of the sugar by one. And we've actually made two different sugars here. And this is what's known as the Kalani-Fisher synthesis. So you can actually make longer sugars through this Kalani-Fisher synthesis. And then imagine that you could actually take this one and do it again. So you could start with a 3-carbon sugar and build a 4-carbon sugar, and then build a 5-carbon sugar and a 6-carbon sugar. This is not how our bodies do it. Our bodies are much more efficient. But in the lab, if you needed to make some sugars, this would be a fine, although very laborious route. So the Kalani-Fisher synthesis, the key is we're adding a carbon from a nitrile. We do it by making cyanohydrins under a little bit of acid catalyzed conditions. And again, we make two stereocenters there. We do a Lindler-like reduction, so we want to use a poisoned catalyst. That's what this barium sulfate is. It's poisoning the palladium, so it only adds the H's once, so we don't reduce it all the way down to the amine. We reduce it down to the imine, and then we just do the imine hydrolysis to get to our aldehydes. And from erythrose, a 4-carbon sugar, we actually make ribose and arabinose. And notice the relationship between those. They only differ at one stereocenter, so we've made epimers. So we now have two epimeric sugars that differ just at the C2 position there. known as the Kalani-Fisher synthesis using chemistry that we've seen before. Now this reaction here is referred to as the wool degradation, and I just think it's amazing because someone just took the Kalani-Fisher synthesis and said, let's run it in reverse. And if you run the Kalani-Fisher synthesis in reverse, you should actually make the carbon chain shorter. Just like if you play a country record in reverse, you get your dog back, you get your house back, you get your car back, and you get your girl back. If you run the Kalani-Fisher synthesis in reverse, you should get a sugar back that has 1 carbon less. And so the procedure for doing that is actually the reverse. We first take and make an amine. Now this is a special type of amine. It's actually called a hydroxyl amine because we're actually using hydroxylamine right here, amine. And this is a oxime. Sorry, this is what that functional group is called. It has this OH out here. And if we take that OH and mix it with acetic acid, you can actually convert these oximes here into nitriles. And notice that when we mix it with acetic acid, we actually make esters on every single one of our OHs. That's chemistry that we just talked about. So what you've done is you've converted all those OHs into acetyl groups. And then what we do is we go and deprotect those acetyl groups. And then what we do is the reverse of the cyanohydrin formation. We deprotonate that H, collapse that down, and kick out the nitrile. Again, chemistry that we talked about in the aldehyde and ketone chapter. We talked about how cyanohydrins were reversible under basic conditions. What we do is we kick out the cyanohydrin and we just get back our carbonyl. Under acidic conditions, we actually favor formation. So this wool degradation is, again, just the reverse of the Kalani-Fisher synthesis. We make this imine or oxime. We actually take acetic anhydride, convert it into a nitrile. And then what we do is we kick that nitrile out. The Kalani-Fisher synthesis is we first make this cyanohydrin, we reduce it down to an imine, and then hydrolyze the imine. So to me, this is amazing that they're using the same chemistry. It's just the order of operations, which step you do. And so you can either build up the sugar or break it down. So the Kalani-Fisher synthesis and the wool degradation. So let's talk a little bit more about this mechanism of actually how we convert a oxime into a cyanohydrin. When you react your sugar with the acetic anhydride, what you actually do is you convert that oxygen off the oxime into a ester-like derivative. And then when you add a base, I'll just make a general base. What you do is do an E2 elimination, and you kick off this acetate, which is actually a decent leaving group. So the key is you convert that oxime into this ester-like compound, and then when you mix it with the base, you kick it off and kick off that ester, and that's how you get the nitrile. And then finally, when we keep it in base, it will reverse the reaction of the cyanohydrin, and we get back our carbonyl, and we've shortened the chain by 1. Okay, so some other reactions that we can do is I've talked briefly just about reducing sugars and oxidizing. And so what we can do is we can actually take advantage of sugars. And as we talked about previously, they tend to be in their cyclic form, but they do exist in equilibrium when we put them in water with their open chain form. So if you happen to take glucose or glucopyranose or dextrose, all the same thing, and put it in water, you'll get a small amount of the open chain form, roughly 1%. Actually, I think it was 2% for glucose. But that doesn't matter, because what we're doing is we're exposing it to sodium borohydride. And as soon as it opens up, the sodium borohydride is going to reduce down that carbonyl and give us an alcohol. And then the ring doesn't close up because we no longer have a carbonyl for that center, or that Stephan center, to close up. So essentially we lock it in the open chain form. And what we've gone from is an aldohexose to just an alcohol. And these are referred to as alditols. So the key there being alls, we've converted them into an alcohol. They're also generally known as sugar alcohols. In fact, if you have a pack of sugar-free gum sitting around, and I've got some in my drawer, so I'll pull it out, and if I read the first ingredients, it is sorbitol. If I read later on, I will also see mannitol and some other artificial sweeteners in there, but these are artificial sweeteners. They taste sweet to us, but since we don't have this carbonyl on there, our body can't metabolize them. So these molecules right here are artificial sweeteners, non-nutritive, because we can't process them because of the lack of the carbonyl there. And so there's a bunch of them out there that you'll see: erythritol, mannitol, xylitol. These are all artificial sweeteners, referred to as non-nutritive sweeteners or sugar alcohols. They also have some other properties. Back in the day, Ex-Lax actually used to use phenolphthalein, the indicator from your Gen Chem experience that turned pink in basic solutions. So phenolphthalein used to be a laxative. I guess there was some issues with it, and now if you buy Ex-Lax, you'll actually see that it includes sorbitol as the active ingredient. If you watch House, or you happen to follow the reviews of the sugar-free gummy bears on Amazon, you'll find out that if you happen to chew too much sugar-free gum or eat large amounts of Haribo sugar-free gummy bears, you will have an Ex-Lax-like experience, because sorbitol is a laxative. And how that works is it's non-nutritive, it's not absorbed, and it's an alcohol that loves to be solvated by water or dissolved in water. So if you happen to have lots of sorbitol, it tends to pull water out of your intestines to keep it hydrated. And if you're pulling water out of your intestines, that, let's just say, lubricates the system and does what Ex-Lax does. So don't chew too much sugar-free gum. And if you happen to eat sugar-free gummy bears, eat them in moderation. Again, this is the reduction. This is done at an industrial scale. And again, they convert nutritive sugars, things that we can actually get energy out of, into non-nutritive sweeteners. And kind of interesting, these polyalcohols tend to be sweet to us. So ethylene glycol, which is actually antifreeze, if you happen to go and taste it, would taste sweet to you. It also tastes sweet to dogs. And so that's why they actually tell you to keep antifreeze away from dogs, because they'll, they get a taste of it, they will eat it and it will kill them, as well as kill humans. But typically humans aren't into eating antifreeze. Unless you happen to kill a spouse, then what you can do is include antifreeze in Jell-O and make sure that your spouse is eating Jell-O. They'll start to get sick, and the only thing that they can keep down is Jell-O, and then you can feed them more antifreeze-filled Jell-O, and eventually they die, and you inherit millions of dollars, unless that spouse was smart enough to write a note that says, hey, if I die, open up this letter, and I will explain that it was probably my spouse that did it. Anyway, true experiences out there, spouses killing each other over using this ethylene glycol. It does taste sweet, but it is toxic. Now, cats, being the smarter of the animals, actually don't have this issue. So they're smart enough not to eat antifreeze. And that's not because they're smart. They actually lack the receptor for sweetness, but they do enjoy eating earwax. So maybe they're not as smart as I think. Okay. So I talked about reducing sugars, and that previous example, even though we reduced the sugar, is not what we're talking about. So we did reduce the sugar, but what a reducing sugar is it's actually a reducing agent. So dig back deep into your Gen Chem. If we have a reducing agent, what happens to the molecule? It gets oxidized. So glucose, again, if we put it in water, will open up into this aldehyde. And as I showed you on the previous slide, we can reduce that, but it can also get oxidized if we have an oxidizing agent. If we have an oxidizing agent, then by virtue of redox reactions, this becomes the reducing agent. It's oxidized, but the role that it plays is it's a reducing agent. So a sugar can actually play the role of a reducing agent and become oxidized in the process. So one way that we can do that is mix it with just bromine and water, and we can convert the aldehyde into an acid. The sugar becomes oxidized, but it acts as a reducing agent. So we can take glucose, and it would open up again in solution and get oxidized. So if we have these hemiacetals, they are referred to as reducing sugars because they are acting as reducing agents, thus getting oxidized. So one of the interesting reactions is known as the Tollens test. So you can actually take beta glucose, and if you take the Tollens reagent, which is listed over here, it's actually a silver salt, dissolved silver. What happens is the aldehyde gets oxidized. So therefore, glucose is acting as a reducing sugar and getting oxidized in the process. Well, if the sugar is getting oxidized, something has to be reduced. And so what's getting reduced is the silver ion. And so if you remember, if you get reduced, that's gaining electrons. And so this silver ion turns into silver metal in the reduction. And when it turns into silver metal, it actually will plate glass. So this is how they used to make mirrors, is that you would take a solution of a reducing sugar like glucose, take this Tollens reagent, mix them together. The silver actually gets reduced and the sugar gets oxidized, and then the silver plates out and makes a mirror. So this is the Tollens reagent. So there's some other tests. So if you ever wondered how they figured out that people had sugar in their urine, well, the first way was you would taste it. And if the urine tasted sweet, then that person had sugar in their urine and may have diabetes. Another test, since the lab techs didn't necessarily like tasting urine, was made by Phaline or Benedict. And so in this reagent, what they did, or this reaction, what they do is they take copper ions, which are blue, and would do the same reaction. We would oxidize the sugar that's in the urine, and the sugar becomes oxidized, but the copper becomes reduced and changes color into brick red. So what you do is you'd mix someone's urine with this blue copper solution, and if it turned red, they had sugar in their urine, and that would indicate that they have issues. You're not supposed to have sugar in your urine. Now you can actually oxidize both ends of a sugar. Oh, sorry, I should go back and say these sugars that are oxidized at one end are referred to as aldonic acids. So once you converted it here, it's no longer an aldose, it's an aldonic acid. If we oxidize both ends, we convert that sugar into what's known as an alderic acid. And nitric acid will actually oxidize both ends of a sugar, and you get alderic acids. So we're not worrying about mechanisms here, just that we can actually oxidize sugars there. So even ketoses that you look at that and say, ooh, there's no way to oxidize a ketone. Well, ketones can actually be oxidized, and we actually have to do some chemistry first. And this reaction actually takes a little bit longer. So you can actually do these tests to determine if you have a ketose or an aldose. Aldoses tend to react fairly fast. So they're fast reducing sugars. They get oxidized fairly fast, where ketoses actually react much, much slower. And the reason for that is we have to undergo a conversion or an enolization tautomerization. And so what we do is we first enolize the ketone to get the enediol. And then once we get the enediol, of course, we can tautomerize and convert a ketose into an aldose. So if we're doing a test and we have a ketone in solution and it's basic, after a short amount of, decent amount of time, we'll start to get aldoses, and then they can be oxidized and give us a positive test. This just takes longer. So if you throw glucose in solution, you'd get a fast test. If you threw fructose into solution, it would be slow, but it eventually would appear. And so you can identify aldoses and ketoses by how fast they are oxidized or reduced. And so here is that an example. So this is what they used to see. What you do is you'd put someone down in the laboratory in the basement of the hospital. You'd give them urine samples, and they would add the Phaling's test or the Benedict's reagent into the urine. And then they'd heat up this over a nice Bunsen burner. You can just imagine this. They're probably in a basement with no windows, heating up urine all day over a Bunsen burner, looking for conversion into the red. And depending on how red it turned, you could actually tell how much sugar they had in their solution. We now have much easier ways to do that avoid lab technicians tasting urine or heating up test tubes of urine. But the process is still the same. You're still oxidizing the sugar. And so again, fructose, that originally you look at it and say, well, I can't oxidize that because it's a ketone, can be converted into this enediol and then give you epimers of glucose and mannose that are readily oxidized. So again, these are all referred to as reducing sugars because they get oxidized. Okay, I think we're going to stop there. That's a lot of chemistry, but I give you a hint of what we'll talk about next time to finish up the chapter. Is I talked about how we can form acetal linkages with alcohols. And a great alcohol to form an acetal linkage would be another sugar. And so we can actually form these acetal, or like I said in biological terms, glycosidic bonds between two sugars. And so this now becomes a disaccharide. So we'll use that glycosidic bond formation to now talk about disaccharides and polysaccharides, and that will be the last section. And so we'll stop it there, and we'll bring you some more sweet chemistry knowledge in the next lecture.